Hi, my name is Murphy, and this is my presentation over the power management system discussed in Knowledge Integration 1. I'm in all three of the ECE courses, 311, 331, and 341, so my presentation will pertain to all three courses. Here is our power management circuit. There is a rectifier / RC circuit connected, and there's a V in, a V rec, and a V out that we will be discussing. So the diode bridge from the 311 perspective will show us if it is nonlinear and time invariant, and it turns out that it is nonlinear and time invariant. So looking here at the math, we have a sinusoidal input wave and a sine squared output. And when we do x1 with t equals -1, we get the inverse in orange for x2 of t. When we put that into the circuit, we do not get the inverse of y1 of t. We end up getting almost the same thing as y1 of t. So it turns out that it fails the test of homogeneity. And it also fails the test of additivity, because when you add this x1 of t to the x2 of t, you end up getting 0, but when you add the 2, or the y1 of t and the y2 of t, you get 2 times y1 of t. So it's failing nonlinear in both cases. We are going to test for time invariance by shifting the input x of t by a time t0, and it turns out that y of t is shifted by the same time of t0, so it is time invariant. Then from a 331 perspective, we're going to see that the threshold voltage increases as average power increases. So here in blue we have the ideal diode output, and the actual diode output is in pink here, and it is lagging the ideal diode output by VD on, and yet our threshold voltage is usually around 0.7 volts, and it is the internal resistance inside the depletion region of the diode. So we want this depletion region because as VT goes to 0, our depletion region goes to 0, and then it would just become a silicon bar, and we want a diode. So say we have 3 different diodes with different doping quantities, and we get VD on is less than VD on of 2 is less than VD on of 3, and you get this output V rec of T shown below, and then you can see that the average power for V1 is greatest, and the power lost is least, the same as the electric field is least. So then from the 341 perspective, we're going to dive a little deeper into this electric field that occurs across the depletion region, and this is opposing the current going across the depletion region, which causes this internal resistance. We're going to find the E field by integrating the charge density for the P and the N regions, and then we are going to integrate that to find the voltage. So here we can see a plot of the charge density per distance on the P and N junctions. On the left we have the N junction, on the right of the plot we have the P junction, and we use planar symmetry and Gauss's law to find the E field, and that is plotted in the blue and purple plot on the left. And then we integrate it, which is on the bottom here, and we can see that our voltage is VD on equals 2 times V0 because we have 2 diodes active at any time. Now from a 311 perspective, we're going to look at the RC circuit. We find out that it is linear and time invariant, and this is because when we take the equation of this RC circuit here on the right, you get this function here, which is a linear constant coefficient differential equation. This quite explains the nature of the circuit, but we're going to test for linearity and homogeneity, or homogeneity and additivity anyway for linearity, and then check if it's time invariant. So when we plug in A times x1 of t equals y2 of t, we know that y2 of t equals A times y1 of t, and it ends up being homogeneous. Then we test x1 of t plus x2 of t to see if y1 or y3 of t equals y1 of t and y2 of t, and that ends up being true, so it is additive and therefore linear. We know that there are no initial conditions, so the system is time invariant. Now from a 331 perspective, we're going to see that V out is a ripple voltage that lags V in of t by 2 VD on. So you can see here in the positive half cycle we have two diodes active and a current going through R1. And we're going to know that as soon as the voltage or the diodes turn on, that Vrec is going to lag Vin by 2 VD on, as we discussed before. And so this blue line here shows that until it meets the Vrec voltage, and then it decays linearly. And this is across the capacitor. And the reason that the capacitor decays linearly instead of exponentially in this case is because when we take the Taylor series approximation of the decay, we know that every polynomial of 2 in power greater is going to go to 0 because when you square such a small value, it's going to just get smaller and smaller. So we end up with this line. Then from a 341 perspective, we're going to see that the capacitor behaves differently at different times t. And this is shown here. At time equals 0, we get a short across the capacitor because the impedance goes to 0. And then at time equals infinity, we're going to get an open across the capacitor because the impedance becomes infinite. And so we get a voltage divider for V out in this case. And then we have our two blue line plots here that we add together, and we end up getting this pink line for V versus T. And we know that our tau is C times R equivalent for an RC circuit, and this will be our output. Overall, our circuit is going to be nonlinear and time invariant because the rectifier was nonlinear and the RC circuit was linear, and it ends up making the whole thing nonlinear, and then both were time invariant. So thank you very much, and that was my explanation of the power management system from all three classes' perspective. Thank you.